We will now start a brief theoretical part on statistical tests. The aim of this part is definitely not to teach you the deep theory which lies behind the statistical tests, but to give you an idea of how statistical test works in such a way that you can understand the meaning of the results that I will display to you and how can you interpret them. Okay, we will not explain the theory as usual, but we will go straight forward into an example. This is the easiest test that exists. Statistical tests are a family of several tests, all with the same, let's say, structure. This is the easiest test that exists. It's student t-test for one variable. And I will show you straightforward an example from which you can understand the test structure. Okay, let's start. Suppose, for example, that we want to study the age of internet users. Okay. First of all, we make an hypothesis. Our hypothesis is that here I call expected value, but average age. The average age is 35. Okay, so our hypothesis, average age of internet user is 35. Well, in theory, you could check it directly. You just find out all the ages of all the internet users of the world and calculate the average. Well, it's a task which is far beyond any researcher possibilities, okay? Especially because new users appear while you are calculating the average, new users will appear. So what do? Instead of investigating on the entire population, which is impossible or too much, we take a sample. Okay? We have a sample of 100 users. Pay attention that in every statistical test, in theory, the sample must be completely random. In practice, it's very difficult to build a random sampling, especially a random sampling of people, because some people don't cooperate. So there are techniques to adjust the sample when it's not random, but in theory it must be perfectly random. So a sample of 100 users, okay? We ask these people their age, and here are the result. 100, we have practical one variable called age with 100 cases. The variable is obviously scale, okay? Even though it's discrete because nobody says 20,5, but it's scale anyway. Okay, I put the variable just for simplicity here in Excel. Okay, so I have 100 cases. Okay, let's see, what will you do to check whether the average of the population from which the sample comes is 35? Well, what every person will do is calculating the average on the sample. So you have your hypothesis, average age. Expected value, it's basically the average on the population. Okay. Average age on population is 35. On population. So the average age calculated on the entire population is 35. The age calculated on the entire population is not 35. Now we calculate the average age of the sample. Well, Excel, you should know, has a wonderful function called average. 36.2. Okay, so the average age on our sample is 36.2. It's an estimation of the average age population's age. Okay. Okay, so we have 36.2 on our sample. However, our hypothesis was that the average age on the population was 35. There is a difference of plus 1.2. So we found on this sample is slightly older than what we expected. Now we ask ourselves this important question, which is crucial. This difference of 1.2 is larger, and this means that the average age on the population population's age is not 35, okay, and that therefore we must reject H0 and H1 will be the correct hypothesis, or the average age, the difference of 1.2 after all is so small that it may be due to random fluctuation of the sample. Maybe we were unlucky in the sample choice and we didn't choose a sample which was so precise. There was maybe one person older and therefore we must accept H0. So take into consideration that the average age of the population may be 35. Well, probably many of you will say, well, 1.2 years of difference, you reject. Well, and I now change the question. Imagine that instead of plus 1.2, you get plus 0.2. If you get plus 0.2, do you reject or do you accept? And if you get plus 0.5, plus 0.6, okay, so we must find out what is the tolerance. It's almost impossible to get a sample whose average age is exactly 35. You must be extremely lucky. Okay, so for sure you will never get a sample whose average is exactly 35. So you will get a sample whose average is slightly different, but up to which difference do we confirm the H0 hypothesis, and starting from which difference do we reject the H0 hypothesis? So we must find a number which is a trade-off between too small and too large. Okay, so how can we do? Well, the majority of people, and I see this regularly in newspaper and magazine, decides just with a subjective decision, say, well, 1.2 too much, so the average age is not really 35. Or 1.2 after all, it's not so much, average age is 35. Okay. There are also people who adjust their H0 hypothesis and say, okay, the average age is 36.2, but this is something horrible. Okay, in statistics, we have a tool which helps us finding out whether the average age is the average age on the population is 35. So 1.2 is after all small and we have simply been unlucky, or whether average age is not 35 and 1.2 is not so small. Okay, so in statistics we have a measure of how unlucky we have been. Okay, this measure is called significance. Significance, the probability that H0 is not false. Okay, with a high significance, it means that we have not been, so with a high significance, it means that we have been unlucky. Okay, and so the average age may be 35. With a low significance, it means that we have not been unlucky. The difference is 1.5 because the average age on the population is not 1.5. So in statistics, we have this significance which measure how unlucky have we been. Okay, with a small significance, it means that, well, the probability that we have been unlucky is small. So the reason of the difference lies in the fact that the average age on the population is not 35. Okay. With a high significance, it means that the probability of having been unlucky is high, and so 1.2 derives from an unlucky choice of the sample. Okay. This significance is calculated through a statistical function, through computer truth tables, which traditionally are written at the end of the books, or a computer program. So it's calculated through complicated method, which I don't want to explain here. What is important for you is that in the test you have your H0 hypothesis and your H1 hypothesis. The test is like a machine which, given you data, produces a significance. Okay? If the significance is large, you accept H0. It means that you have been unlucky. It means that in this case, your average is different from what you expect, but only because you have been unlucky in your choice of the sample. If the significance is small, on the other hand, it means that the probability that you have been unlucky is very small, so probably you are not unlucky. Probably the reason of the difference lies in the fact that your H0 hypothesis is wrong, and thus you reject. So significance large, you accept; significance small, reject. Okay. In this specific example, I calculated the significance, okay, and I got 16%. And now I ask the same question again. Is 60% large or small? Well, 60% is large. Right? In statistics, typically 5% is the trade-off. So below 5%, the significance is small. Above, it's large. Some researchers tolerate also 10%. Other researchers want 1%. Okay, but usually 5%. So below 5%, significance is considered to be small. Above 5%, significance is considered to be large. So in this case, we will accept. It means that, okay, our average was not exactly 35, it was something different, but this may be due to a bad choice of the sample, so an unlucky choice of the sample, because sample is random. So we never make a bad choice, an unlucky choice of the sample. Okay, at this point, we have everything. So we know how you have the data, you put the data inside this machine, you make an H0 hypothesis, you put the data inside this machine, which crunches your data and gives you a significance, and the significance tells you whether to accept or reject the H0 hypothesis. So the mechanics is pretty easy. What you have to understand conceptually, however, and it's very, very important, it's written here, is that if you reject, since your significance is 5%, if you reject, it means that you are really almost sure that H0 is false. Okay? It means that you have only 5% of probability of having been unlucky and 95% of probability that your H0 is false. So if you reject, you are very sure of what you're doing. Okay? So when you reject, you can say average age on the population is not 35, almost for sure. Okay. On the other hand, if you accept, please don't say average age on the population is 35. Well, I know that from a linguistic point of view is a nonsense, because you accept and you cannot say it. But because when you accept, first of all, because you have a significance of 5%, so you don't have a significance of 80%. But second, because when you accept, it means that your data don't tell you anything to contrast the H0 hypothesis. So please, when you accept, it means that you don't know. So you have not proven anything. So statistics is a destructive science. So it's a science designed to destroy your H0 hypothesis. You have basically no tool to confirm your H0 hypothesis. So statistics is a science which can destroy things. It's very good for destroying things. You have your data, you say, well, this data don't conform with the theory, so the theory is wrong. But you have no way to assess something, so to confirm something, because imagine that you get average age on the sample of 35.2. You probably will accept, okay, for sure, 35.2. But this does not prove that average age is 35. It may be 34.9, 35.1, 35.3, okay? And all these hypotheses will be accepted. So while rejecting is a strong thing, accepting is not. When you accept, it means that your data are not able to tell you anything. Okay, so please don't conclude we accept H0 and therefore the average age of the population is 35. No, statisticians say, and therefore we cannot reject that the average age of the population is 35. Okay, well, we cannot deny that the average age of the population is 35, but we're not sure. It may be 35.2, for example. Okay, so after this important distinction, there is another slight important distinction. Well, it's a particular case. Whenever you have a very small number of cases, and with very small I mean, for example, 10, well, I am pretty sure that almost all your statistical tests will accept. Because whenever you don't have enough cases to destroy a theory, the statistical test very simply accepts. Okay? So the statistical test rejects only when it's very sure that the H0 hypothesis is wrong. When it's not sure because the data are somehow close but not so close, and or you don't have too many data, the statistical test automatically will accept. Okay, so if you are doing in your future a research on a sample of 10 people, well, probably all your statistical tests will accept. So don't even do them because it's silly. Okay, and now we will start talking about statistical test using R. We will start with statistical test for one variable, so univariate. I build here a small table which tells you what you have a variable. Okay, when we have already seen numerical description and graphical description. When the variable is nominal, frequencies, bar plot, we have called it column plot, I think. Column plot. Even though in R probably the name is bar plot. Scale, descriptive statistic, histogram, and box plot. Okay, so this is the, let's say, the descriptive part. Let's see the parametric test. Okay, I will explain later the difference between parametric and non-parametric. However, there is no parametric test for nominal variable. The only parametric test for scale variable is student t-test for one variable. It's exactly the test that we have talked right now. Okay. So let's see how to do the student t-test for one variable in R. Okay, first of all, oops, I call it always expected value, but it's average on the population. Okay. The H0 hypothesis is that the average on the population be equal to a certain value m that you decide. Okay, so let's take as an example the usual age. Well, I don't remember which was the average age of our sample. Let's say that we make the hypothesis that on the population the average age is 40. So statistics means single sample t-test on age, alternative hypothesis H1, population different from mu0, 40. Press OK, and you get your data. There are a lot of data. The meaningful one for you are, well, first of all, the sample mean, which is 43. So you see there is a 3.87 of difference. Now I ask myself, is this 3.87 difference can be attributed to bad luck in the sample choice, or is it really that the average on age of the population is not 40? Well, with a p-value equal to 2e minus 0.6, do you know the meaning of this e minus 0.6? It means that you have to move the point of 6 places to the left. So this becomes 0.00000267. So it's very, very below 5%. Okay. And so we reject H0 hypothesis. We are sure that the average age on the population is not 40. Okay. Well, let's make, which variables do we have? Let's see. Other scale variable. The weight and the height. Let's make the hypothesis that the average weight be, well, given a quick look here, be 80, rather high. Let's say 75. Or H0 hypothesis average weight is 75. Statistics means single sample t-test. Weight. As you can see, doing this kind of test is easy with a computer. It's like a machine. You put the data in, you push a button, brush, you get the significance. However, pay attention because you must be able to understand the significance and understand the null hypothesis. Our null hypothesis here is average weight on the population is 75 kilograms. Crack, 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 crack. Well, first of all, the average weight on the sample is 73, so not so far away. In fact, we get a p-value which is 0.09. It's above 5%, so we accept. This means that the average weight on the population is 75. No, no, absolutely no. This means that the average weight on the population could be 75. We have no data to deny it. Okay. So we accept, thus we have no data to deny the hypothesis that the average weight on the population be 75. Okay. Okay, so you have understood it's pretty easy. You just put the things inside. The important thing is that you have to look here. Okay. Well, also look here, but just to get an idea of what's happening. Look here, your significance. Know when to accept and when to reject, and note the meaning of accept, which is not that H0 is true. Okay, so statistical test, student test for one variable, it's pretty easy. Okay, there is another interesting test, which is exactly the same one, but on the median. Okay, they're called sign test. However, it's not a variable in our command. It exists inside R. It's called sign, but I don't want you to deal with a text interface, so it's unfortunately not a variable in our command. Okay, let's go to nominal variables. For nominal variable, we have the very famous chi-square test for a one-dimensional contingency table. Okay. So how does it work? Do you remember the one-dimensional contingency tables are basically the frequencies? So let's see them. For example, frequency distribution of Marischal. Okay, this thing here. Okay, something we have seen when we were talking about just taking an overview on univariate variables. Okay, so you have your nominal variable, which is split into 20% here, 70% here, 7% here, 2% here. Okay. Now I make something similar to the previous test. My H0 hypothesis is that the classification, which means the frequency distributions, follows a predetermined distribution, which I decide. So my H0 hypothesis, for example, is that single married people are 30%. Sorry, single married people are 75%. Married people are 75%. Single are 20%, and we are already at 95. Divorced 5%, and widowed 0. Or let's say divorced 4% and widowed 1%. Okay, so my hypothesis is different from the sample. Theoretically, it's not allowed to look at the sample and then make your hypothesis. You're cheating if you're doing like this. In theory, you should have your hypothesis in mind before starting the research. Okay, so suppose I have in mind, I will write it here. Have in mind, this is the trick to write comments. My H0 hypothesis is that single are, let's say, 25%, married 75%, not too much, too many. Okay, divorced 4%. Okay, suppose that at the beginning of the research I have this hypothesis. Okay, I want to test it. Well, first of all, after having stated my hypothesis, I take a look at the situation of my sample. I see, it's not very similar because this says 69 is different from 75. But let's do the test. Maybe the difference is due to bad luck. Okay, so statistics. Where is the test? The test is in the same place as the frequency distribution. Probably you have already noticed it. Marisha is here. Chi-squared. Op. If you flag it, when you press OK, it will ask you for your hypothesis. Well, it starts if you don't say anything, it supposes 25, 25, 25, 25, but here we have 0.2. Remember, always use the point, even if your Windows separator is the dot, sorry, is the comma. Oops, 0.04. Okay, press OK. Let's see. First of all, it repeats the same thing that we have already seen. Then it makes the chi-square test. Well, the numerical value of the test is not important for you. It's just a complex calculation. But the important thing is the p-value. Look, p-value very small, well below 5%. It means that we reject. It means, therefore, I can write here the conclusion. Conclusion, H0 rejected. We are sure that single is not 20% or married is not 75%, and probably this is the ones which had the tail failed, or divorced is not 4%, or widowed is not 1%. So this test checks the entire classification. If just one of the thing is wrong, so for example, in this case, probably it was married, which were not 75%, the test will reject. I repeat, it's not considered moral to look at the sample and then make your hypothesis. Okay? Even though I'm pretty sure there are a lot of people who do it. But you should first make your hypothesis and then look at the sample. Otherwise, too easy. I make my hypothesis identical to the sample. Oh, okay. Let's do another one. Another one with a variable with two categories. For example, bruxism. I suppose 10% of the people have bruxism and 90% of the people don't. So this time I don't, sorry, H0, 10% of people answer yes. To bruxism. Okay. This time I don't even look at the frequencies before, so I do everything without cheating. Statistics, summaries, frequency distribution. Where is bruxism? Chi-square, flag it. By the way, if I just ask for frequencies, I don't want to see in the exam this one flagged. So if I see that you automatically ask every time for the chi-square test, I will mark it as a partially wrong. So don't do the chi-square test if it is not a test part, if it is not required. Not half and half, I hope. Yes, 0.1 and no, 0.9. I think that you must take care yourself that the sum makes 1. P-value 67, so we accept. It does not mean that the distribution is this one. It means that we accept H0 and therefore it can be that have don't. Okay, it can be, it could be even better. It could be. So we have not, in other words, we have our data. Do not deny that 10% of people have bruxism. Okay? It's if you write we accept and thus H0 is true, I will mark it as wrong. These are comments. Whenever you start with this thing, it's a comment. Even if you press submit, it doesn't do anything. Okay, so these are the tests that we have. By the way, what's the difference between a parametric and a non-parametric? Well, you have seen student test was on the average, on the mean. Sign test was on the median. The difference is that the parametric test apart from the technical difference, which I don't want to explain here, but the practical difference that the parametric test usually have to deal with the values, so the numbers. The non-parametric tests have more to deal with the position. The average, you know very well, it's calculated using numbers. You have to sum up all the values and divide by the number of values. The median, on the other hand, doesn't have to do really with numbers. You just look how many elements are on the left and how many elements are on the right. So still has something to do with numbers, but more with order rather than with number. So usually the parametric tests have something to do with number. In particular, most of the time they talk about averages. So it's a test on the averages. The non-parametric test is the test on the position. The sign test was a test on whether the center of the distribution is. This one was a test on which how much of cases fall into this category, how much of cases fall into the other category. Okay, this is the difference. You will see much better later on when we start talking about bivariate analysis technique.